So our VTEPS project is called the Drip Drop. Our mission statement was to create an accessible automatic plant watering device. This will be aimed at college students or people with busy lifestyles. Using those ideas, we created a customer profile. Our ideal customer will be people with busy lives who will benefit a lot from saving time doing everyday things. Doing things such as watering their houseplants. We then conducted multiple surveys and we created a customer needs table. Through this table, we found out that people often forget to water their houseplants. They are concerned about the health of their houseplants and they want a solution that is aesthetically pleasing. We also developed a list of product specifications that we would want our project to ideally have. So ideally, we will want our project to have a battery life of around 2 months on standby. We will want our project to be able to water a houseplant for around 9 days. And we will want the form factor to be able to fit within a 3x3 inch box. After that, we broke down our problem using the black box method. So we divided the problem into simple inputs, outputs, and functions. So for our material input, we only need the input of water. So then we will need a refillable system that will be able to store our material input of water. This water will need to be transferred from the storage to the plant. For our energy input, we have both electrical energy and gravitational energy. So the electrical energy will be used to power our microcontroller and our moving mechanism. The gravitational energy will be what allows the water to flow from our system to the plant. We will need a way to store the energy. This will then need to power the water delivery mechanism, which will draw water from the storage to the plant. Our signal input will come from our users. Our users will set a certain schedule for the plant watering. This signal will then be translated to certain settings that will determine when the energy will be powering the water delivery mechanism. So the signal will determine when the power will go to the system that will deliver water from our storage to the plant. So then after that, we created a concept combination table. So we listed 5 sub-functions that our final project will need to have, and then we came up with around 3 to 4 potential solutions for each sub-function. So our sub-functions are receive power. So this is how our project will receive and store power. So we came up with 3 solutions for that. A wall outlet, which will plug directly into the outlet of your house. A battery pack. So this is a battery pack that will need to be recharged intermittently. This battery pack will power the rest of the system. We also have a solar panel. So the solar panel will be mounted on our project. This will not need to be recharged manually, but this will need to have access to an area with sunlight. So our user interface sub-function is how our users will be interacting and setting the settings for our device. We came up with 4 solutions: a display with buttons, a touchscreen, a display with a remote, or an app or a website that will be controlled on an external device like your phone, your laptop, or anywhere else. Our third sub-function is the water dispensing mechanism. We came up with 3 solutions for this: a constantly dripping water nozzle with a small hole. This nozzle will constantly dispense water, and we will control the amount of water it dispenses by controlling the size of the hole and also when it opens and closes. A timed flow system is a gate that will open and allow water to flow through and will close after a certain amount of water has flown through. A pump system is a pump connected to a water source. This pump will then be programmed to pump a certain volume of water and then this will go directly to the plant. So our form factor subfunction is how our final project will look like. So it could be stuck into the soil. This solution means that our device will be stuck into the soil of a potted plant. A freestanding box is a box that is on a separate area as a plant, and this will connect to the house plant using some sort of pipe. Hanging off pot lid, this form factor is a small module that can be hung on the side of a pot, and a sticky form factor. This form factor will have an adhesive on the side of a module, so similar to the hanging pot lid module, but instead of a hanging system, it has an adhesive which you can stick onto the wall or onto the pot itself. Finally, we have the water storage subfunction. So this subfunction will be how we store the water inside of our project. So we have three potential solutions. So a separate tank, which is a tank that is separate from the module itself. This tank will be able to refill, and it will be drawn upon to water the plant. A direct tap will not have a tank. Instead, it will be connected directly to a tap in the house. This will not need to be refilled, and this will directly draw water from the water system in your home directly to the plant. An integrated tank is similar to a separate tank, but instead of being on the side of the module, the tank will be stuck onto the module as one piece. So the module and the tank will be one device. This tank will also need to be refilled. So after coming up with our subfunctions and our potential solutions, our team uses the 6-3-5 and a 3-2-1 method. So combining each solution for a subfunction, so a unique solution, so a unique combination for each, we came up with two potential solutions each. Each of us also drew a mock-up design of what the project can potentially look like after we create it, and this will represent what our final project can look like if we go through with this potential solution. So then we compiled all of this into a gallery method presentation. We then received feedback from other teams, and Team 14 brought to our attention the possibility of mold as well as the structural integrity of our device. So because our project will be dealing with mold, or we'll be dealing with water, there's a possibility that mold will grow on our project. This will not be good for the environment as well as the plant itself. Our solution for this potential problem is to use a plant-safe cleaner and a nozzle that is hard for the mold to grow on. The other problem would be the structural integrity of our project. Because we will be storing a lot of water, the water may add a lot of weight that we did not prepare for, and then the weight of the water could then compromise the structure of our system and make it so that it does not work as intended. So our solution to that problem is to use a strong material as well as a high amount of wall thickness and infill for our 3D prints. So then after we came up with our 8 potential solutions, we screened all those potential solutions using a concept screening table. So we listed each potential solution with a letter in the alphabet. We then came up with 7 selection criteria. We also took a reference solution, which is an already existing product that is out on the market, and then we compared each of our potential solutions with the reference. So depending if our potential solution is better, worse, or neutral in a certain criteria, we listed it as a positive, a negative, or 0. So our 7 selection criteria were ease of use, ease of refill, ease of handling, manufacturing, aesthetically pleasing, watering accuracy, and longevity. After evaluating all 8 of our potential solutions, we decided to go through with solutions A, B, C, and H. Because solutions A and C were really similar and they had traits that could benefit each other, we decided to combine solutions A and C into one. So then after deciding to go through with A, B, C, and H, we scored these solutions using a concept scoring table. So the concept scoring table is similar to the screening table, except each criteria is now weighted by the importance that we determined for our final project. So for our final project, we determined that the criteria of ease of use and watering accuracy were the most important criteria. This is because we want our users to be able to use our product without any hassle, and we also want the watering amount to be accurate as to not overwater or underwater the plant. Our reference was also put in the scoring table and given a decently neutral score of 3. We would then, using the weighted criteria, we then assigned each potential solution with a score from 1 to 5, 1 being the worst, 5 being the best. So after evaluating our 3 new potential solutions, AC being the combined combination of 2 solutions, we decided to go through with one of our highest ranking solutions being AC. We decided to go through with this system because although it is not the best rated, we deemed that it was the best, it was the most realistically possible solution. So after going through our mock-up for projects A and C, we combined those ideas and we made a non-functioning mock-up. So this will only determine what our final project can possibly look like, and this will not be functional in watering any houseplants.